Connection between a moving wave packet and classical particle is developed by Ehrenfest in 1927. He proved that in the limit when the wave packet associated with a particle reduces to a point, the particle behaves like a classical particle. To prove it, let's consider one-dimensional motion of a particle of mass m. The expectation value of its position is given by this expression integral minus infinity to plus infinity psi star operator x psi dx. Its time derivative is then given by dou by dou t of all these quantities. See here I have written x instead of operator x as the position operator acting on the wave function returns the position eigenvalue x. And now this differential is equal to integral minus infinity to plus infinity. If you differentiate it, you will be having two terms like this. In the first one, we take the time derivative of psi star alone and keeping x psi constant, and then you have to differentiate psi keeping psi star and x as constant. Since operators are considered as time independent in Schrodinger representations, we do not need to take the time derivative of x. We have seen that the time derivative of wave functions can be written like this by rearranging the Schrodinger equation. So if we make these substitutions for time derivatives of wave functions in equation 1, we get this expression. The potential energy terms actually cancels each other, so there is no potential energy term appearing in this expression. Now let's consider the first integral in this expression and integrating it by parts, taking x psi as the first function gives us this result, first function into differential of the second function minus integral of the derivative of the first function into the differential of the second function. Now since the wave function vanishes as the limit goes to infinity, this term goes to 0 for both the positive and negative limits. Integrating the second term once again by integration by parts, we get this expression. In this also, this first term goes to 0 because of the same reasons as the wave function, and its derivatives has to go to 0 as the limit x goes to infinity. Now if we consider this differential part alone, we get two terms, dou psi by dou x and x dou square psi by dou x square. So we have ultimately an equation integral minus infinity to plus infinity x psi dou square psi star by dou x square dx equal to integral minus infinity to plus infinity 2 times dou psi by dou x plus x dou square psi by dou x square, then this psi star dx. Here these second and third terms get cancels each other, and hence it gets simplified as something like this. Here you can see that the quantity inside the bracket is the operator form of linear momentum px. We will learn more about operators in the coming classes. So hence this equation can be written as 1 by m integral minus infinity to plus infinity psi star, and in place of this operator minus ih cross dou by dou x, we can just write the operator form of linear momentum, which is px, or this can be rearranged as m into d by dt of expectation x equal to the expectation value of the linear momentum. So in the limit the wave packet reduces to a point, the expectation x is simply x itself and the expectation px is simply px, and then this equation becomes simply as m into dx by dt equal to px, which is the classical expression for the linear momentum of a particle with mass m moving at a speed dx by dt. Next, let's consider the rate of change of expectation value of the linear momentum, and the expectation value of linear momentum is given by these expressions, and we have to take the time derivative of these things. This is given by this expression. You can take this minus I h cross out of this integral, and then you have to differentiate the remaining two terms. So first you differentiate the psi star with respect to time, keeping the other term constant, dou psi by dou x, and then we keep psi star constant and then take the differential of this term dou psi by dou x. Again we substitute for the partial derivatives of psi and psi star from the Schrodinger equation, and that will give us an expression like this. This can be further simplified like this after rearranging the terms, and in this final expression these two terms get cancelled each other. So out of remaining terms, this middle term can be written in terms of differential of psi star dou square psi by dou x square like this. Here the first two integrals becomes 0 as the wave function and its derivatives vanish at infinity, and the last integral is the expectation value of the gradient of potential energy. Hence the derivative of x component of linear momentum simply becomes the expectation of negative gradient of potential, which is nothing but the expectation of x component of the force acting on the particle. When the wave packet reduces to a point, it simply becomes this form, which is the Newton's second law of motion. So we can generalize equations 4 and 5 to get the three-dimensional equations like these. Now these are the quantum equivalent of the equations of motion of classical particle and is called the Ehrenfest theorem.